In this video, we're going to prove that between any two real numbers, you can find a rational number. Another way of saying this is to say that the rationals are dense in the reals. This is sometimes called the density theorem. The proof of this theorem will rely on the Archimedean principle and a corollary to it. So recall that the Archimedean principle says that for any real number, you can find a larger natural number. There's an easy corollary to the Archimedean principle that says if there's a real number r, then you can find an integer n less than it. Okay. So the Archimedean principle says given any real number, you can find a larger natural number. And the corollary says given any real number, you can find a smaller integer. We'll use both of those during the proof. So to get started, we're going to prove a lemma. The lemma says that if a and b are real numbers, and a plus 1 is less than b, then there's an integer m so that a is less than m is less than b. Okay. So to prove that, let's assume that a and b are real numbers, and let's assume that a plus 1 is less than b. Let's look at the set capital A, which consists of all integers k that are larger than a. So a is a set of all k in z so that a is less than k. Now by the Archimedean principle, given any real number, such as a, we know we can find a natural number larger than a. Okay, so the Archimedean principle guarantees us a natural number n so that a is less than n. In other words, that tells us that the set capital A is not empty. Okay, it has at least one element. Now by that corollary to the Archimedean principle, we know that we can find an integer p less than a. Okay. So what we're getting at here is that we have the set A, which is non-empty. It's a set of integers which is non-empty, and it has an integer lower bound. It has a lower bound p. Okay. So A is a set of integers with at least one element and at least one lower bound, and we know something about such sets of integers. We know that they have to have minimums. So that means that we have a minimum element for the set A. Let's call it m. Since m is a minimum of the set A, we know that m is an element of the set A. And if x is in the set A, then m is less than or equal to x. We will reformulate 2 to say that if something is less than the minimum of A, it's not in A. So if x is less than m, then x is not an element of the set A. Now, since m is in the set A, and A is defined as a set of all integers k so that a is less than k, we know that a is less than m. Okay? So m is one of those integers that are larger than a. M minus 1, though, we know that's smaller than m. So m minus 1 is smaller than the minimum of a. So it can't be an element of a. And if m minus 1 is not an element of a, that means that a less than m minus 1 is not true. Okay, a minus m minus 1 is not true. And so that means, by trichotomy, that m minus 1 has to be less than or equal to a. Alright, well that tells us that m is less than or equal to a plus 1. And recall that a plus 1 is less than b by assumption. So transitivity tells us that a is less than m, is less than or equal to a plus 1, is less than b. So in particular, a is less than m is less than b, and that concludes the proof of the lemma. So now let's prove the density theorem. The density theorem says that if you have any two real numbers, a and b, with a less than b, then we can find a rational number between them. So we can find an element r in the rationals q, so that a is less than r and r is less than b. So let's assume a and b are elements of the reals, the real numbers, and let's assume a is less than b. That means that b minus a is going to be greater than 0. All right, and in particular, it's non-zero. So it has a multiplicative inverse. So non-zero elements of ordered fields have multiplicative inverses. In this case, we're in the reals. That multiplicative inverse is 1 over b minus a. So that's a real number. It's a well-defined real number. By the Archimedean principle, we can find a natural number that's larger than that real number, so we can find a natural number n so that 1 over b minus a is less than n. And recall, b minus a now is positive, so a is less than b, so b minus a is positive. That means we can multiply by b minus a on both sides of that inequality, and it'll preserve the direction of the inequality. So b minus a times 1 over b minus a is going to be less than b minus a times n. And of course that means that 1 is less than bn minus an, so b minus a times 1 over b minus a is 1. And on the right hand side, b minus a times n, if we distribute that, that's b times n minus a times n. And that tells us, by adding an to both sides, that an plus 1 is less than bn. Okay, so an is a real number, a is a real number, a times n is a real number, b is a real number, so b times n is a real number. So now we exactly have the hypothesis of the lemma we proved. We proved that lemma earlier that exactly fits this situation. So we can apply the lemma, all right, and the lemma tells us that in this case we can find an integer between the real numbers an and bn. So we can find an m so that an is less than m and m is less than bn. Now n is a natural number, and in particular so it's positive, so we can divide the inequalities by it or multiply by 1 over n to get that a is less than m over n is less than b. All right? And we carefully chose m and n. In particular, we know that m is an integer and n is a natural number, so m over n fits our definition of rational number. And so we proved that between any two real numbers, a and b, we can find a rational number between them. And that concludes the proof of the density theorem. That means the rationals are dense in the reals. Thanks for listening.